Hi, I'm Brian from Simply Brian Enterprises, and welcome to my channel. Have you ever heard the Chinese proverb, if you chase two rabbits, they'll both get away? Well, that's kind of what's happened to me the last couple weeks. I've been trying to simultaneously work on Pi Pico homework and Pi homework and haven't made a lot of progress on either. And so my homework solution for TopTechBoy's Raspberry Pi Pico class lesson number 5 is long overdue. So with that in mind, let's take a look at the hardware and talk about this week's lesson. So in lesson number 5, Paul challenged us to wire up a potentiometer to our Pi Pico and then use a Python program to return values with the math equations that he showed us in class. So before I show you the board, I just want to show you my pinout card here that came in your Pi Pico Kepler kit. And I'm using pin 31, which is GPIO 26 and ADC input 0. Um, Wonderful card. I love having this handy. I just leave it right there pretty much. So I got an idea after watching one of BBF's videos about normally when I do jumper wires across the board, I will just run them straight across, basically the shortest path. However, BBF was illustrating how using longer jumpers and putting these nice clean 90-degree bends in them can actually make the board just as clean and give you a lot more room to work. So I thought that was a neat idea. I'm going to try that going forward and see how that pans out. So thank you, BBF, for that piece of advice. As far as the wiring goes, it's pretty straightforward. I've made some design changes to my breadboard, and I think you may have seen them in previous weeks. I just haven't talked about them. Initially, I had all of my rails over here at 5 volts. They were all coming off of my power supply. However, I've decided to make a change. Um, the I still have a 5-volt rail here and a 5-volt rail here that come off the power supply, and that's going to be for when we drive things like servos or we use some higher powered devices and we want that 5 volts right off of the adapter rather than trying to pull all that current through the Pico. But in this case, we want 3.3 volt in. So what I've done is I've wired the 3.3 volt output to a rail, and I've done the same with my other Pico. And of course, then I put labels on it. So you can see I've got a 5-volt rail and a 3.3 volt rail. The 5 volt is always hot. The 3.3 volt is only hot when the Pico is powered. So I've got my potentiometer wired to the 3.3 volt rail for this project because I want to send 3.3 volts into the GPIO pin. You'll notice I also have on the left side I'm wired to ground, and on the right I'm wired to 3.3 volts. Every potentiometer is different. I actually have some potentiometers that are backwards from this, where when you have the wiper at its lowest point on the left, it actually reads, in this wiring configuration, it'll read high instead of low, which is kind of backwards because you'd think if the wiper is pointing to the negative side that it would read low. But for some reason, internally, it's actually wired backwards, and this is high and this is low, so I have to reverse the polarity. So it's always a good idea when you're wiring these up to give it a test first and make sure that you have it wired correctly. A couple other things we need to know about our potentiometer is we need to know its minimum and maximum values. So if I turn this all the way to the left, what is the value that I read on the Pico? If I turn it all the way to the right, what is the value I'm going to read on the Pico? And it's important to note that every every potentiometer is going to be a little different. The tolerance and the manufacturing with these, um, Paul gave us his numbers, but mine are probably going to be a little bit different just because of variations in manufacturing and so forth. And then there's one other thing we have to consider, which is the question of whether or not we're looking at a linear potentiometer where the value increases at a constant rate as we move from left to right, or if it's a logarithmic type, because there are logarithmic potentiometers out there where the value will jump as you start moving right, and then once you hit about halfway, it starts to taper off and it stops increasing at the same rate. So we have to think through all of these things about which type do we have. So to start off with, we're going to run a very simple program which looks suspiciously like Paul's because it pretty much does the same thing as Paul's. I'm going to turn all the way to the left here. And we'll start running the program. And we see that our value is somewhere below 200-ish. And as I start to move it to the right, that number increases pretty drastically. And then if I turn it all the way right, we get 65,535, which is the maximum value of the 16-bit counter. So we kind of have our boundaries um, somewhere in the neighborhood of about 200 to 65,535. Now, we want to determine whether or not this is a linear or a exponential, or a logarithmic, I should say. And the way we're going to do that is we're going to calculate our center value. So in a linear potentiometer where the rate of change is consistent through the whole motion of the wiper, we're going to be about half the distance between the low and the high. So 65,535 minus 200, that gives us somewhere in the neighborhood of 32,500. So we would expect, if it's linear, to see a value of about 32,500. But if it's logarithmic, when we get to the center, let's say we just kind of assign random values from 0 to 10, and we make the center 5. Well, the log of 5 is about 0.7. So if it's logarithmic and we move to the center, it's going to be the minimum to maximum times 0.7, which from my math gives us about 48,000. So I'm just going to bring this back here. And actually here, I'll go to this view so you can see that the potentiometer is near the center. And then once I have it to the center, I will flip back. That's not centered. I gotta find center here. There we go. Trying to look at the screen and the potentiometer. So that looks pretty close to center. And when we flip back, we see a value of about 29,000. So maybe I could be a little closer to center. Let's see if I can get that closer to 32,000. But that would tell us that this is a linear potentiometer, because if it was logarithmic, we'd see in the 45,000 range. Let's see how far I have to turn it to get to 45,000. And we'll back it off a little bit there. 40. That's pretty close to 45,000. We can see it's at about 2/3, which is where we'd expect it to be. So this looks like it's a linear potentiometer. So now that we know that, we can start to do some math. I'm going to just flip to this view quick so we can switch my highly technological graphics here. And we're going to look at some math. So Paul gave us the example of kind of translating that minimum value and that maximum value to calculate voltage. Now, voltage is going to be a linear value, and it's going to have a positive slope, because as we're all the way to the left, we have a lower x value, but we also have a lower y value of voltage. And then as we go to the right, voltage increases. But Paul gave us the task of, let's decrease that. Let's go all the way to the left, we're at 100, and all the way to the right, we're at 0. So that gives us a negative slope. So now we have to start thinking through the same math, but we're going to do it backwards. So we start off kind of the same way. So I used 170 as my minimum. In testing, I found out I need to use a slightly larger number, but for the math we're going to do here, we'll use 170 as my minimum value, and 65,535 is my maximum. And of course, at the lowest value, I want to register 100, and at the maximum value, I want to register 0. So I start to work through that, and I start to plug in into my y equals mx plus b equation, and I start to calculate the slope. X2 minus x1, 65,365. Y2 minus y1 is negative 100, and it's negative because the slope is downward rather than upward as x increases. So that gives us this slope of negative 100 over 65,365. Then we use the distributive property. I'm just going to flip this around here. Actually, I can probably just get rid of this piece of paper at this point. We use the distributive property to multiply that by x and multiply that times b. So we end up with this negative 100x over 65, 365, minus negative 100 times 170. So um, we have our y2 minus y1 value times the lowest value over, again, that differential of 65, 365. Now that's y minus 100 equals all of this. So of course, in algebra, we have to add 100 to both sides to even it out. So I started to think, what is this number really? We can use, the exact value of negative 100 times 170 over that, but what is this actual value? And we do the math, we find out that this is about negative 17,000 over 65,000, which equates to about, zero point 0.2, zero point 0.3-ish. So it's a very small number. And then we're going to add 100 to it. What that tells us is that our y-intercept is going to be 100 plus maybe 0.2 or zero point 0.3. It's going to be a very small differential between this point and the y-axis. So when we kind of look at it that way, let's just have a little check I did to make sure that I had this math correct. It didn't look right at first, but then when I started to do the math, it started to make sense. So then I'm going to plug in, instead of x and y, I'm going to add in this numeric value, or num_val, as y and pot value as x, and take the same equation. So if we look at our code and how we're going to translate that, let's flip over to this value. So here we've got our pin, GPIO pin 26. And as I mentioned, I used 170 in the math earlier, but really what I found is that 300 gives us a better resolution. And I also did pot max a little less than 535. I did it at 530. And then I just did this pot diff of max minus min. That way, the only variables I have to change are the minimum and the maximum. Everything else just kind of falls into place as we go through the code, and I don't have to modify anything more. I'm going to read in my value. I'm going to define my potentiometer, and then I'm going to go into my while loop and read the value every time through the loop. Now, we haven't talked about if statements yet, but I wanted to set some boundaries, because as we saw when I ran the initial program, we can go 300 is a good low number, but we often drop below that, like even into the 90s. So what I want to do when we drop that low is I actually want to rewrite that value to basically discard it. If it's below 300, let's just call it 300. We're not going to try to do the math of going lower. So what I'm saying is, if it's less than the minimum, let's just write the value as the minimum. If it's 90, let's rewrite it as 300. And then we do on the same on the top end. And actually, that's why I changed this from 535. I'm going to move my mouse cursor. 535 to 530 is because I want to do this little change here of saying, if it's greater than that maximum, let's just clip it off and let's just call it the maximum instead of trying to go over. That way, when we display this value between 100 and 0, we're not going to get outside of those values. So in the same way, we're going to calculate the voltage. I figured if we're already calculating values, let's grab the voltage as well. And this is very similar to what Paul showed us. It's the 3.3 times pot value over the difference minus 3.3 times the pot minimum over pot diff. So it's basically the same equation Paul showed us. And then my equation in the same form here, let's go back to this. So I've got negative 100 times pot val over pot diff minus, and then we get this kind of, where's my arrow key? There we go. Negative 100 times pot min over pot diff. And again, that comes out to about 0.2, 0.3. And then we're going to add 100 to get our y-intercept. And then I'm taking this value and I'm actually converting it to an integer, because if we're going to go from 100 on the low end to 0 on the high end, let's make that an integer so that it looks nice. And then I'm just printing all three values together, sleeping for half a second, and then looping again. So let's run that. Here, actually, let's get this all the way to the left. And we're going to go ahead and run this code. And we see that we have all the way to the left, our value is 300, our voltage is 0, and our numeric value is 100. So now I'm going to start bringing this up. And we can see the voltage is a floating point, so it's kind of taking up some screen space there. Let's get it to about halfway. Let's see if I can land this right on 50. Let's see if I can hit 50. There. Got the potentiometer, so we've got exactly what we would expect. We've got a value of about 32,000, a voltage of about 165, and that value was 50. It's bouncing around now. These things are sensitive. All right, so now we'll keep going all the way up, and as I turn up, we get closer and closer and closer to 0, and we end up at 0, 3.3 volts. So I hope that that was helpful. I know that there were some people kind of concerned about the math and doing the trigonometry and so forth, but it's really not that difficult once you do it a couple of times. The y equals mx plus b equation is it's pretty straightforward once you grasp that. So if you didn't get it, keep at it. It's not that hard. If you like this video, be sure to hit like and subscribe below. Appreciate the comments, appreciate the subscriptions. And for Simply Brian Enterprises, I am Brian. See you later. Thank you for watching.